All right, so we're going to begin with a slideshow that's just a discussion of the definite integral. So I'm going to go ahead and launch the slides and mostly just talk about it. Okay, we'll turn this on. Okay, so the indefinite integral, remember we had to introduce some constant that we didn't know what it was, and unless they gave us some sort of a constraint, we weren't able to figure that constant out. We're going to work with something called a definite integral now that integrates between a lower and an upper value. So down here we'll start at A and we'll integrate up to an upper limit of B. So lower limit of A and an upper limit of B. And the picture right here shows us that the definite integral is going to be the area bounded by the curve of f of x. So imagine this little slope. This looks like a big hill. And if we imagine that function, then the definite integral is going to be the area bounded by the function on top and the x-axis below, and between the vertical lines x equals a and x equals b. So let me see if I can get my pen here. So, okay, so for instance, if a started right here and b ended right here, then we would only be talking about, if that was A and this was B, then we'd only be talking about the area bounded from here to here. If I moved B down here, then it would encompass that much area. So we have some point where we start, we just drop a vertical line and chop it off there, and where we end, we drop a vertical line, and then that basically creates the bounds for the area. It's kind of hard to see if this was A and if this was B. And so what we're going to do is explore why that's the case in these next few slides. Okay, so let's say that we don't have, we want to get as close as we can to an area, but really when we calculate areas, we're pretty good at it in algebra with just straight lines. So if I want a rectangular area, I know how to do that. We know how to calculate areas of triangles. So most shapes that we have straight lines, we can calculate. But if we have a smooth curved line on one or more sides of the shape, then it's a little more difficult. What we do instead is we'll kind of estimate it by putting these straight line shapes, in this case rectangles, below the curve. And the way that we do that is, if you think about it, and we split this up into 4 rectangles, so that's why they're calling this L4. What the L stands for is left side, and the 4 subscript stands for how many rectangles we create. Now the reason this is a left side calculation is because the top of the rectangle is the left, is where it touches the curve on the left side. So if I were only calculating the area of this one here, if I were only interested in that area, that's this. F of 1 is right here, right? Because that's where we're on the graph at F of 1. So that's the height of my rectangle. So height times width, and width is just how what our delta x value is going to be. So here we've established that we're going to change x by 1. So I can take delta x times f of the left side, and that calculates the area of L1. Now if we jump here and I take, let me get my pen back, not what I wanted. Okay, so now if I take f of 2, that's where I touch the graph on this one, and this is still delta x, our change in x, which we said we're just going to count by ones. So if I take the height f of 2 times delta x, now I've added this rectangle in. Okay, so that's what L4 is. I'm going to calculate 1, 2, 3, 4 areas of rectangles just by using a simple length times width. Okay, and this says, okay, well, the area under the curve between 1 and 5 appears to be about 23 square units. But you can see we're off by these amounts here that didn't get calculated in. So these little triangular looking things, but they're not quite triangles because that's a smooth curve. Okay, so let's move on with this. And what that is an estimate of this integral. Okay, we can do it the other way, and this time we're going to change it to an R. So R means that I'm going to take the right side of the rectangle and where it touches the graph, so that becomes f of 2. And then we use f of 2, f of 3, f of 4, and f of 5. And we still use delta x. But then we call that R. So that's going to be, if we calculated these, then that would be the sum of all these areas. So notice that this time, instead of underestimating the area below that curve, we've overestimated it by these little portions here. So I'm kind of identifying the overestimate. So if you look at the first value from the left side, we underestimate the actual area. And then if we do it on the right-hand side, then we overestimate the area. So if we take and average our underestimation and our overestimation, average it and divide by 2, we're going to get an even better approximation of the integral from 1 to 5 of 0.5 x squared plus 2. And that's what this dx right here is the delta x. All right. So this is like the height, and dx is the width. And we're taking the integral. Okay, so just imagine what's going to happen here if I keep shrinking the size of delta x, or if we make dx infinitesimal, that's a hard word to say, infinitely small. Then what's going to happen? Okay, so the actual area, although we estimated it to be 29, the actual area under that curve is 28.6 repeating, which is pretty accurate. And here it's just telling us that if I let delta x get smaller, instead of using delta x counting by ones for the width, we could make it 0.05, really small. Then we're going to create a lot more rectangles, but we're also going to get a lot closer to the actual value by chopping this up into finer rectangles where our overestimation and our underestimation gets a lot less pronounced. Okay, we also know that, and it's possible that our left side calculation could be an overestimation and our right side be an underestimation. Just imagine this curve going down. But either way, the area that I estimate with the left side calculation and the area that I estimate, one is an overestimate, one's an underestimate, so the actual area is squeezed in between those two areas. Okay? So this tells us if f is a decreasing function, then we would have to change our inequalities, because it's possible that this could be the overestimate. Okay, that's all this is saying. All right, so remember our idea of limits here. If f of x is increasing or decreasing on a, b, oops. So say this is a and this is b down here. So this would be f of a, and that would be f of b. All right, so then its left and right sums approach the same number as n goes to infinity. Another way to think of it is if my delta x goes to 0, is the same, essentially the same, because if n is the number of rectangles, well, for that to go to infinity, then I have to make the delta x value between them start to approach 0, because if I split this up into an infinite number of rectangles, okay, so the left and right sums start to approach the same real number. So what it's approaching is the actual area, the actual result. Okay. Okay, so this is some really finely constructed jargon describing essentially what we just did. So note that if n goes to infinity, that means I'm splitting up the number of rectangles between my start point A and my end point B. And that means that delta x is getting smaller. Well, this is just telling us that we don't necessarily need each delta x to have the same exact width. So we call this S sub n. Okay, so if we take the sum of the area of the rectangle, so let's describe what's going on here. For each C, which is just the subinterval between xk minus 1 and xk, so it's an arbitrary point. Okay, so instead of using left or right, S just represents an arbitrary point between k minus 1 and k. So essentially, like this is a left side, this is a right side, and S could be any place between the left and right. So it's going to come up here. So it doesn't matter where we get our F. Since we're going to create so many of them by letting n go to infinity, they're all going to squeeze together. And we call this a Riemann sum. So the summation of these as n goes to infinity breaks these into smaller and smaller width rectangles. Okay. So the area under the curve is approximated by this Riemann sum. All right, so that sets us up for the definite integral. If f is a continuous function on the interval from a closed interval from a to b, then the Riemann sums for f on ab approach a real number I as n goes to infinity. And that limit itself on AB is called the definite integral of f from a to b. And guess what? It's the integral from a to b of f of x times dx. So the integrand, that's just saying that the a is the lower limit and the b is the upper limit of the integration. Okay, so this gives us some terminology. I think I want to switch over now. Yeah, I do. Let's switch over. And I'm going to shrink this dude, go away. Okay, so let's put these new ideas to use. Okay, we've already said that the definite integral is on a continuous function from a to b. The limit of Riemann sums of f on a to b is guaranteed to exist. It's called the definite integral, and it's denoted as integral from lower bound a to upper bound b of f of x times dx. So the integrand is f of x, and the lower limit is a, and the upper limit is b. Now, we said that it calculates the area under the curve, or the area between f of x and the x-axis. So if you notice this, if we took the integral from, this picture here says a lot. Okay, so A is the area of this little section in gray. B is the area of this section in light blue. The integral starting at A and ending at B of fx dx is actually negative A plus B. So if f is below the x-axis, then the integral, the area is calculated as a negative. And if it's above the x-axis, the integral calculates the area as a positive. So if I wanted, for instance, the area to be calculated for both of these, I've got to know what this point is here, where it changes from a negative area to a positive area. Okay, so we're going to use this result, and we know that this changes over at a place called 0 and a place called B, and just based on these values here, we're going to be able to answer A, B, and C. So let's look at A. A wants the area from A to B of f of x dx. Okay, well, from this here, we can see that that equals the opposite. So it equals negative A plus B plus negative C. Okay, stop me if you don't see why that's the case. Okay, so A is the actual area as a positive quantity. Since I'm integrating between A and 0, I know that this is going to be equal to negative 2.33 plus B. Now that's going to be positive because it's above the x-axis, so that'll be 10.67. But C is an area below the x-axis and between the curves, so that's going to be once again a negative, so we'll add negative 5.63. So the integral from all the way from A to, this says from A to B. Well, I'm going to fix this by erasing this. I did not do A. Sorry, I misread that. I was thinking it asked already from A to C. So we're going to call this example Z, whatever. Okay, so if I actually wanted the area, or not the area, the areas are given here, but the integral from A to C has to be calculated by taking the opposite of whatever that area is. That actual area would be positive, and then since this is below, it's going to be negative again. Okay, so if I calculate that out, okay, that equals 2.71. Okay, so if I took that integral. Now, if let's go ahead and do A now. All right, A was a little less ambitious than I got here. It says just give me the integral from A to B of f of x dx. Well, that corresponds to negative A and positive B, so that's just going to be negative 2.33 plus 10.67. Okay, so that's going to be 8.34. Okay, so we actually did B. All right, so I did them in the wrong order. We're going to do C, which says give me the integral from B to C, f of x dx. Okay, so that's going to be just this portion here between B and C, so that's going to be negative of the area C. So that's going to be negative 5.63. All right, so what I'm going to do, just to kind of drill this one last idea home, let's say that we want all of the areas represented. Let's make an integral that adds up to the sum of all these areas. So if I add those together, I get 2.33 plus 10.67 plus 5.63, 18.63. If I actually wanted to create intervals that add up to the area represented by the shaded region, this would have to be the opposite of the integral from a to 0, fx dx, because since it's below the x-axis and the curve, it's going to come out negative as the integral. So if I want a positive area, I have to negate it. Don't have to do anything between 0 and b because it's above the x-axis there. So that'll just be plain old integral from 0 to b fx dx. Then I'm going to have to negate again between b and c. Okay, and essentially that would give me the result 18.63. Okay, so it's kind of an introduction to the definite integral. Let's look at some properties and then we'll apply them. Okay, so the first property we're going to look at, if I take the integral from a to a, well, not surprisingly, there's no area because we haven't advanced at all, so that's just going to be 0. And if I go from a to some other number b, fx dx, I'm going to get the opposite result as if I switch the numbers and move my upper limit down here and my lower limit up here. And that was kind of illustrated on the last page, not directly, but kind of indirectly, that notion was obtained. Next one, if I got a constant, well, we already learned this. This is a carryover from indefinite integrals, so they're just saying this also works for definite integrals. If I have a constant, I can take it on the outside and do my integral and multiply the constant. This also is a carryover. It says if I've got multiple terms, I can separate them out and treat each in its own integral. Okay, so we've seen that. Now, if b is some number between, so we're going to assume for number 5, if we go from a to c and it's equal to a to b, okay, so I can take this from a to some intermediate number between the two and split it up that way if I want to. All right, so based on those properties, we want to be able to calculate some of these. Now, we don't have a graph, but they're telling us that for a function x, the integral from 0 to 2 of x dx equals 2. If I go from 0 to 2 for the function x squared, the integral from 0 to 2 of x squared dx equals 8/3. And if I go from 2 to 3 for x squared, I get 19/3. Just using these properties and these known areas under the curve of these graphs between the function and x and bounded by lower limit, upper limit. Okay, so for a, we do have something that takes us from 2 to 3, and it's 19/3. So we know from this constant rule that the integral from 2 to 3 of 6x squared dx is equal to 6 times the integral from 2 to 3 of x squared dx. And we can just substitute that 19/3 here, so we equal 6 times 19/3. So it equals 38. Okay, let's look at B. If I want to go from 0 to 2, for 9x squared minus 4x dx, well, I'm going to use a couple of these over here. First, I'm going to say, well, that's the integral from 0 to 2 of 9x squared dx minus the integral from 0 to 2 of 4x dx. Furthermore, I know from the constant property that that's 9 times integral from 0 to 2 of x squared dx minus 4 times the integral from 0 to 2 of x dx. So let's just start substituting. So 9 times 0 to 2 of x squared is 8/3. Minus 4, 0 to 2 of x is 2. So it's going to be 24 minus 8. So 16. Okay, any questions how I got that? Let's move on to C. Okay, C, we're going from 2 to 0 of 3x dx. Well, we don't have anything that takes us from 2 to 0 for x, but we got something that takes us from 0 to 2, and we got a rule that says if I switch the a and the b around, I can negate and get the same result. So this would be equivalent to the opposite if our bounds, upper and lower bounds, switch places. 3x dx. Oops. So that would be equal to -3 integral from 0 to 2 x dx. And we're just substituting the 2 for integral 0 to 2 x dx. So that equals -3 times 2, or -6. Okay, let's take a look at D. That's going to be our first property. If I don't change from my lower limit to my lower bound to my upper bound, then I haven't created any width at all. So we're going to get 0. All right, last one. So we're going from 0 to 3, 12x squared dx. Okay, notice that we don't have any 0 to 3s for x squared dx, but if I go from 0 to 2 and then 2 to 3, I can split it up and effectively get from 0 to 3. And since our property 5 says I can do that, if I go from all the way from A to C through an intermediate, I get the same result. So we're going to go ahead and split this up and make it integral 12x squared dx 0 to 2 plus integral 2 to 3 12x squared dx bring the 12 out here. And now I've got it in terms of something for which they've given us the areas. So it would be 12 times 8/3 for 0 to 2 x squared plus 12 times 19/3 for 2 to 3 x squared. Okay, so 4 times 8 and then 19 times 4. Okay, so we know how to take integrals, but we're not worried about that for this section. What we're worried about is understanding the properties of definite integrals. And then next chapter, we'll actually learn how to take definite integrals. We know how to take the integral without a lower and an upper bound if those weren't there. And we'd have to plug in our constant of integration. In the next class and beyond, we will learn how to do the definite integral and what do we do with these, because we're not always going to be just given the area. We're going to have to calculate it ourselves. By the end of next class, we'll know how to get this and figure out that it's 19/3 without them telling us. Okay, so I've got an assignment just for you guys to get kind of practiced on understanding the area, calculating the area under the curve. And just remember that if f is above the x-axis, then the area between f and the x-axis, the integral will be, the integral associated with it will be positive, and the area below the x-axis and above the curve, of course, an area is positive, but if you integrate between those values left to right, you'll get a negative of the area. Okay. Any questions before you guys embark on that? I think there's maybe 10 or 12 questions at most, exercising these ideas.